Welcome back. We are in the next lecture in Fundamental of Electronics. We were discussing the different rectifier circuits. The next topic that we will take is basically the filtering of the DC output using the choke input filter. So the choke input filter were previously widely used, but now they are very less common due to their cost, the bulkiness and the weight. So we are not using the choke input filter now for numerous applications, and we have some other type of filters which we will discuss in the coming lecture. However, it is useful for the understanding of the other filters that we are going to discuss using the choke input filter. Choke input filter consists of AC source, and then it derives the current through the inductor, capacitor and resistor. So we have one inductor which is connected in series, capacitor which is connected in parallel to the load resistor, and you will be having the output voltage in the load resistor. So the reactance equation, because the inductor will be again frequency dependent for the inductive reactance and the capacitive reactance. Inductive reactance is given by omega L, so which is equal to 2 pi f into the inductor value, and the capacitor value is equal to given by 1 by omega c. So capacitive reactance is 1 by omega c, where omega is 2 pi f. If we talk about the characteristic of the choke, so the inductor is known as the choke, which opposes the change in the current. We know that the voltage of the inductor is given by L di by dt. So the property of inductor is to oppose the change in the current. Because the current is a function of time t, so the inductor will be opposing the change in the current. Ideally, it should reduce the AC current in the load resistor to 0. So if you have any AC current which is going to the resistor, in the ideal condition, the inductor will make it to be 0 because it will not allow the sudden change in the current. So there are some design requirement which we will follow, such as the capacitive reactance and input frequency much smaller than the load resistor. So we can think of the XC value is very less than the RL value, the load resistor. If we do that, then we can ignore the load resistance as given in the circuit number B. So we have removed the load resistor from the network and we got a new circuit because the XC value is very less than the, whereas the design number 2, we have the XL, which is the inductive reactance here, XL, much greater than XC and the input frequency. So we can say that XL is very greater than XC. In this case, the AC output voltage approaches 0. So we do not have any output voltage in the AC condition. The DC current, if we talk about, then the choke approximates short circuit at 0 Hz. So you have the di by dt term as 0 as we have the DC current. So DC current means the frequency is 0, so you do not have any choke characteristic, and the choke approximates open at 0 Hz. Capacitor approximates open at 0 Hz. So the characteristic of inductor will be to short circuit and the capacitor will be open circuit, and the DC current will pass to the load with the minimum losses. So whatever the input is coming in the DC condition, the inductor is basically short, capacitor is open, so all the current will pass through the load resistor. So the circuit here behaves as the reactive voltage divider, and hence we say that when XL is very greater than XC, almost all the AC voltage is dropped across the choke. So here across the choke you will be having all AC voltage drop. Now we can write the output equation as the voltage divider circuit. So we have a voltage divider circuit where XC by XL into Vn. This in the denominator we were basically having XL plus XC, but since the XL is very greater than XC, so we can neglect this XC from the equation and we will have the output voltage. For example, if the XL value is 10 kilo ohm, XC is 100 ohm, so we can see that here XL is very greater than XC and the input voltage being 15 volt, then the output voltage whatever we get it is XC divided by XL into the input voltage, which gives to be 0.15 volt. So for the input voltage of 15 volt, the output voltage is 0.15 volt. it means the filter is reducing the AC voltage by a factor of 100. So the AC components are removed from the output characteristic. When we talk about the rectifier as in the circuit using a filter, so the choke input filter, how it is connected to the rectifier, whether it is half wave rectifier, full wave, center tap, or the bridge rectifier, we use basically the superposition theorem to analyze each source separately. You may have multiple sources connected to the network. Then we combine the voltage for the total result. So here we can see that you have a rectifier. The rectifier may be in different forms, and you are connecting one NC filter here, and you have the load resistor RL. So the DC voltage, which is the average voltage, and the AC voltage, which is the fluctuating part, we can see in the rectifier output. So rectifier output, we can see there is a constant voltage, which is the average value or the DC voltage, and the fluctuating part is basically the AC voltage. Then in that case, what happened is that if the RS, which is the resistance of the inductor, so inductor will have some amount of resistance which is associated with it. So here you have the resistance, and XL value is short circuited, so your entire current is passing from RS to RL. So you are having a constant DC voltage of 63.6 volt. So when the AC voltage across the load resistor you have with the component XL very greater than XC, then minimal AC voltage will be producing across the load, and AC component will be given by this equation which we have seen earlier also. So here the rectifier circuit with filter assume the LC network, which can be thought of only one resistor, and the current is flowing from the rectifier to the load resistor. So in the DC voltage consideration, which is at 0 Hz, so DC means 0 Hz, you will be having the XL to be 0 and XC to be infinite. So the series resistance of the inductor will be very less than the RL. So in this case, your RS is very great, less than the RL, and this RS is the internal resistance of the inductor. So inductor will have some internal resistance. Now the output, if we talk about, then the DC component will pass to the load. AC component will be blocked, which is known as the ripple. So ripple is a term which is used for the AC component which is present in the DC. Ripple measured with the help of oscilloscope. So you will be having certain use of DSO, which is digital storage oscilloscope, to measure the amount of the ripple, and this is known as AC coupling. Means with the DC you have some amount of AC present. The disadvantage, if we talk about this type of filter, is basically when you use the power to convert the AC to DC, there is a trend towards low voltage and high current application. At a line frequency or the power frequency, it may require a large inductor. So due to the large inductor, you will have high winding resistance. So these cause significant DC voltage drop, and it's bulky also, which is unsuitable for applications such as lightweight semiconductor circuit. So semiconductor circuits may not be used so when the frequency is at the power frequency or the line frequency, because you will have large amount of voltage drop. So where do we use this choke input filter? We use basically in the switching regulators. So switching regulators generally used in computers, monitors, or various equipment where the frequency is very greater than 20 kilohertz and allows use of small inductor for filtering. So here the inductor value is very small, resistor will also be small, and the power drop will be small. So high frequency circuits like switching regulators, we may require choke input filter. So we have introduced the filtering concept with choke input filter, and the coming lecture we will see other type of filters which will be based on this choke input filter. Thank you for now. See you in the next lecture.